We just talked generally about why Assist AI can be very useful for healthcare providers. Now I want to talk a little bit about how we would actually do it. So we're going to talk about building a rule-based bot with Python. Let's talk about rule-based bots in general. Even now, many chatbots that power health-related and other consumer-facing applications are rule-driven. So we talked about how rule-driven ways of doing things can be quite brittle. For example, in the case of record matching, rule-driven can be very error-prone. However, in healthcare, it's actually more exciting because it mirrors the way clinicians think and are the way clinicians are supposed to make decisions. So in this case, it's not necessarily a bad idea that our bot is rule-driven. With rule-driven bots, a developer hard codes in possible responses at each stage of a conversation or a decision. This is both a good thing and a bad thing. The good thing is it's fairly transparent. You will know exactly what your bot will do with every given set of inputs. On the downside, it can be quite lengthy to code depending on how you do this. While this can seem primitive, it can be very effective in a large variety of situations and also mirrors medical decision making. This is good both because it will provide the same care as a clinician, which is of course our end goal, to make sure that the patient is not disadvantaged by the use of AI. It's also really good because we can find a way to develop the rules without having to hard code them, right? So hard coding rules is okay, but what's really great about a flowchart is we can actually develop it from the data. So in addition to mirroring clinician thought, we don't have to hard code, right? So I will now demonstrate how we would do this without having to hard code. We're going to build a bot the easy way. We're not doctors, so one way to bootstrap a bot is to link it to a machine learning technique that can provide the rules you want the bot to use. Classic machine learning techniques that correspond to this situation are decision trees and decision tree modeling. Decision tree modeling can be used to classify data points based on a series of binary questions. Decision trees are just like flowcharts. In fact, they're flowchart style algorithms. So we're first going to build a decision tree, and I'm going to show you the code for that. It is in the decision tree and bot folder, and it's called Building Decision Tree Bots as a Python notebook. So the first thing we're going to do, as always, is we're going to read in our data and make sure it's clean. In this case, the column names are not stored in the data format, but I have it separate. So I have my column names, I have my heart data, which comes from the Cleveland Clinic, and if I take a look at the head, I see that I have a fairly wide data set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, something like 13 or 14 columns, all trying to predict heart disease type. Now, one thing I want to do is I probably want to simplify for this task. So rather than trying to predict out of 3 heart disease types, I know that 1 and 2 are both variations on the same thing. So I'm going to restructure my data to just be 0, no heart disease, 1 heart disease. So I'm going to just apply a logical filter that if a value is greater than 0.5, it just means a true for heart disease. And if it's less than 0.5, I have a false. So if I then take a look at my heart data again, we can see that in this case I have converted my heart disease type to just be true or false rather than more detail. And especially as a first pass through my data, it's more important to figure out heart disease or no heart disease than which type. And in a real world scenario, you'll probably get much better clinician adoption if you try for a simpler technique and still defer to the clinician on the end result. So this can also just mirror the sociological processes that are going to get your technology adopted. The other thing is some data is missing, and in fact there's just some question marks sort of floating around in this data set. You don't see them here, but if you went further you would. So we're going to just get rid of those. Make sure our data types are all numbers, which they are, other than heart disease. I see I've got a Boolean for my heart disease type, but otherwise I've got a bunch of floats. So now I've cleaned up my data, I've removed the missing values, and I am ready to go. So now what I'm going to do is I'm going to build a tree, right? Which could be almost an impossible task for a human, right? If a clinician were to build a diagnosis tree, I'm guessing that would take seeing many thousands of patients, many, many years of experience, and that's why these things are written down in textbooks, because it's not something you can easily learn. However, if you have the clinical data and you have some Python, you can actually do it very quickly, right? So rather than this nightmare scenario where we might have to code flowcharts from medical textbooks, we can actually learn them from our data. In this case, I'm just going to import tree from sklearn. We have used this module earlier in this video. I'm going to set X as my input data, right? So these are all the inputs other than the heart disease type, and my Y, which is the thing I'm trying to predict, as my heart disease type. I put those in, and then I am just going to run my decision tree classifier. So first I create it, and you'll see here I'm setting a max depth of 3. That's to avoid overfitting. So if you work in data science, you know that the more complicated your model, the more of a danger there is that your model will reflect the exact data you're looking at rather than general truths about the trend you're trying to investigate. So it can be good to say, my model can be no more complicated than X. And one of the ways you do that with a decision tree is you can just say max depth of 3, which is saying you cannot make more than 3 decisions on the way to a diagnosis. And that's probably good, not just to avoid overfitting, but probably because, again, we want to keep our models simple enough that clinicians can inspect them and understand them, and that's a way to gain the clinician trust for the model. So we will run our model and we will fit it, just like this. And then finally, we have a way to visualize these, right? Because it's one thing to fit the model and then we can put in any input and get outputs, but if we can't inspect it, we can't explain it to other people and we can't be sure it's working properly. So we're actually going to use a method on the tree called export graph viz. We export the graph visualization. This actually produces a .dot file, and that will actually help us visualize the tree. So we're going to visualize the tree. We can do that either with graphviz.com. There's also a graphviz module on Python. This is just a standard visualization format, but you can actually see the tree here. So what the tree will show you is it will show you the question that is asked on the top line. It will show you the Gini coefficient, which is a way of saying how informative is this question as a statistical measure. And it will also show you the breakdown of who's going left and who's going right, as in how many. So in this case, it's asking, is my thal less than or equal to 4.5? If that's true, I go left. If that's false, I go right. Now, one thing that's interesting about trees and how they're really flexible is you see on this layer of decision where you've already broken patients up into 2 categories, you then don't ask them the same question. So if their thal was less than 4.5, you then ask about their calcium, whereas if their thal was greater than 4.5, you ask about their CP. So depending on the first question, you can have a different series of questions, and that very much mirrors how a clinician works, right? If they ask you one question and you give them answer A versus B, they're only going to ask relevant questions as they continue, unlike an insensitive non-AI based application. So we're trying to make our application as much like a clinician as possible. Decision trees very much accomplish that. So the beauty of a decision tree, not only is it a beautiful way of thinking about your data, modeling your data, and predicting, but it also can very easily be piggybacked to create a decision bot. And the reason for that is that arguably a tree is already a decision bot. It's already a flow chart. So the decision tree is stored as a binary tree with various arrays storing threshold values, left and right children, and features used to slice the data at a particular node. With a little programming background, understanding how to traverse a binary tree, you can quickly turn your decision tree structure into a medical bot. For background on this, you should probably read up on binary search trees in an introductory algorithms textbook. So that's not something I'm going to cover, but you will see it in the code we're about to discuss. So we're going to look at taking that decision tree we just built very, very quickly, right, in a matter of seconds with a basic data set, and we're going to turn this machine learning result into a bot. And what's really nice about that is we're just going to use the existing data structure and slap some very minimal AI on top of it, and we technically have a chatbot already. So let's take a look at that code. So to recap, we read in some data, right? We read in our data, we inspected it, we cleaned it up, we built a tree, which thanks to the wonderful developed modules of the sklearn library is a matter of a few lines. We visualize that tree, and now we want to build a bot that will just follow that existing tree down the relevant search path to diagnose someone. So how can we do that? Well, the first thing we're going to do is define a function called bot_from_tree, which is going to take that tree model, take the names of our features, and from that be able to generate some intelligent text. Now, this can't just be one function though. This needs to use recursion, and the reason for that is that a binary tree itself is a recursive data structure. That means that when I take a portion of a binary tree, that itself is a binary tree. So when you have a